So now for the calculations of problem 4.4. We want to show that the product of the marginal densities is equal to G1 multiplied by G2. Because by showing that, we have then shown that the product of the marginal densities is equal to G1 multiplied by G2, which is then equal to the simultaneous density. And that means that x1 and x2 are independent, and then we're done. So in order to show this statement, what we have to do is kind of consider f1 and f2, right? We have to consider the marginal densities, f1 of x1 and f2 of x2, respectively. So let's just say let x1 and x2 and r be given, because we need to show this statement for all x1 and x2. Then the density of x1, the marginal density, is given as the integral over the real axis, so from minus infinity to infinity. So the integral from minus infinity to infinity of the simultaneous density integrated with respect to the variable we want to get rid of, so integrated with respect to x2. Now, by assumption in this exercise, the simultaneous density can be split up into the product of g1 of x1 and g2 of x2. So that is what we will do here, because we want some way to include g1 and g2. So here we have the integral from minus infinity to infinity of g1 of x1, g2 of x2 with respect to x2. So since I'm integrating with respect to x2, I can just take g1 of x1 outside of the integral sign, and then inside of the integral, I have the integral from minus infinity to infinity of g2 of x2 with respect to x2. So what is the value of this? I don't know that. It's just some number. And the reason why it's just some number is because right now I really don't know what it should be, because G2 is not necessarily a density, it's just some function. So we don't know what this is. However, we do know that it is well defined, because G2 is a non-negative function, so this integral is at least infinite, so it's not a too weird integral. And the reason why we know that it isn't infinite is because what we have on this side is a density evaluated in x1, and that is not well, actually that may be an infinite value, but however we're safe because this thing here is at least non-negative, and we're allowed to have non-negative infinite integrals. So now let's take a look at f2 of x2. So the marginal density here is just evaluated in the same way as we did in the above, except now we integrate with respect to x1. And what we get is the same expression as above, just with g2 of x2 outside of the integral, and then the integral from minus infinity to infinity of g1 of x1 with respect to x1. So what we have now is an expression for f1 and an expression for f2. And what we want to show is that these two multiplied together gives us g1 of x1 multiplied by g2 of x2. So let's try and see if that is actually the case. So by multiplication, by multiplying, we see that f1 of x1 multiplied by f2 of x2 is equal to g1 of x1, this one here, multiplied by g2 of x2. And if this were all, then it would be really nice, because then we're done. However, we also need to multiply this thing and this thing. So then we also multiply the integral from minus infinity to infinity. I get really tired of writing the infinity sign, so I'll just write r for the real axis. So that just means the same as integrating from minus infinity to infinity. So the integral of g2 of x2 with respect to x2 multiplied by the integral of g1 of x1 with respect to x1. So we're done if we're done now if we can just show that this thing is equal to 1. So the thing that we can do here is we can write, so this is equal to g1 of x1 multiplied by g2 of x2 dot, or comma, since, so we kind of pretend that we know what's going on, since the integral of g2 with respect to x2 multiplied by the integral of g1 with respect to x1, well, we can actually make this equal 1 because, first of all, these two integrals are with respect to different variables, right? So I can put this entire thing inside this integral, since this is just a constant, and then I can move the integral signs out. So what I'll get is I'll have two integral signs. So a double integral of g1 of x1 multiplied by g2 of x2 with respect to x1 and then with respect to x2. And again, what do we remember we have assumed in this exercise? Well, we have assumed that the simultaneous density is given as g1 multiplied by g2. So that means I can plug back in the simultaneous density. And I actually already had an idea that this was the way it was going to work out up here, because we need this to be equal to 1, and we remember that this one multiplied by this one is the simultaneous density, so you kind of can look a bit forward in time already up here. Anyways, we have double integral sign of the product of g1 and g2, so that's just the simultaneous density. So x1 comma x2, and then with respect to x1 and x2. And this is just equal to 1, right? Because what we've done is we've taken a bivariate density and then just integrated the heck out of it. So this is just equal to 1 because whenever you take a density and integrate it in all the variables over the real axis, then it integrates to 1 because the total probability mass is 1. So hence, this product of integrals is equal to 1, which means the end result is that the densities, the marginal densities multiplied together is equal to g1 and g2 multiplied together, which is in turn equal to the simultaneous density. So in conclusion, x1 and x2 are independent.